Section 11.1 we're going to start today is called Basic Notions. A lot of Chapter 11 is really going to be vocabulary. A lot of it is. So we'll move quickly when we can. We will do some diagrams and some explanation when necessary. And there are some examples throughout sprinkled in there as well. So to start with, we're going to talk about the very most basic, which is points and lines. So a point indicates a location or a place, not a size, and it is denoted by an uppercase letter. It's always capital letters used. Now, necessarily, when you draw a point, you draw size, because there's no way not to do that, but it is not there is no width or length, or there's none of that to it, no size. A line indicates length, but not width. Same thing, you can't draw it with no width, so you see that it has width when you draw it, but it doesn't actually have width, it's just a length. It's given, if you're given 2 points, A and B, there is precisely one line through these 2 points. And we name the lines by lowercase letters. And they're often done with script, like when you see them printed in a book or something like that. So you'll see that I used a lowercase k here that looks like it's slanted and italicized and stuff. That's why. Sometimes you'll see them using 2 points on the plane as well. So let's say you had the A and the B. So you could have them written like A and B, like this. And for a line, you'd have that vertical line on top with the arrows on both ends. You guys don't see all my zooming in and out when I'm not doing this like this. But okay, so we have A, B written like that as a line as well. Line segments. A line segment is a piece of a line that contains 2 end points and all of the points that are between them. So that same line before that was AB, if I do the same AB, and put the line without the arrows on the end of it, that's a line segment. That's the notation we use for it. And then array is a subset of the line that has one end point and contains it contains more than one, but another point we'll call B, and it extends to include all the points that go beyond B. So in terms of notation, we write like this. A couple of things to be aware of on this notation is that the arrow tells you which way you're extending past. So this one is the letter B. It says it includes all points that go beyond B, so the arrow does in fact have to go that direction. It would be a different ray if I wrote the letters as B and then A. It would be the ray going the opposite direction actually. And sometimes you'll hear this called, in some places, it's not as common, but sometimes you'll hear this called a half line. So just in case you hear that word used anywhere, it means ray. Okay? Collinear points. First of all, we're talking about points, we talk about 3 of them. So 3 points are considered collinear if they're on the same line. Why would we never talk about 2 points being collinear? Partly. There's more to it though than just that. Any 2 points automatically have a line that goes through them. You can always draw a line between any 2 points. You can't always draw a line between any 3 points, right? So that's why this is a unique term for 3 or more points, is that 3 points don't have to necessarily lie on the same line, but 2 points always will. So we have 3 points that are on the same line. If we have A, B, and C are collinear, we would say that B is between A and C if AB plus BC equals AC. So visually, we're talking about a picture that looks something like this. So here's A. Here's B, because it said it was the one that was between, and here is C. Now, notationally, you may look at this and see that this says A, B, B, C, A, C, and ask yourself, why aren't there like line things on the top of it? Okay? That's actually on purpose. When we do not have that line symbol or the ray symbol or the line segment symbol on top of it, it means distance. This AB with nothing on top of it is considered to be the distance from A to B. So no symbol on top, it actually means distance. What's that?
Instead of the line segment itself, it's just the distance.
Right. The line segment itself would indicate a geometric object. The distance would mean a numerical value. Okay? So those are the differences in those notations. They seem like they're kind of small, but they're used very differently because this is a number. So AB is the distance from A to B, BC is the distance from B to C, and AC is the distance from A to C. And what this equation right here is saying is that if we add the distance from A to B, plus we add the distance from B to C, it will be the same as the distance from A to C if, in fact, they all lie on the same line. If they don't lie on the same line, then that equation won't hold. Okay? All right, intersecting and concurrent. Intersecting lines are lines with exactly one point in common, and concurrent lines are three or more lines that intersect in the same point. So you can see in this diagram right here, we have intersecting lines, yes? But there are no concurrent lines in this diagram because all three of these lines do have some crossings, but they don't cross at the same point. So there are no concurrent lines here, but there are intersecting lines here. In this diagram, I have both. For example, this line that's vertical from E down to D, and this line that's horizontal from D to G, they intersect. Okay, so those are two lines they intersect. But they are concurrent with this line FD because those are three lines that all intersect at the same point D. So concurrent is talking about more than two lines crossing. Okay, does everybody have what they want drawn? Are we good? Okay. A plane. A plane indicates a surface, not a thickness. Okay, again, you can't draw a plane and actually have it have no thickness in your drawing, but it doesn't have a thickness. So oftentimes when I talk about planes, I have sort of visualized my piece of paper, or I visualize the ceiling. But that's not really a plane because it has thickness. It's just a visual imagery for us to get the same sort of idea. The other thing that none of those objects do is they don't extend in all directions forever, right? The ceiling stops, this paper stops, but a plane will extend in all directions forever, or in all of its directions forever. Given three non-collinear points, there is exactly one plane that contains all three of these points. So anytime you have 2 points, you get a line automatically. Anytime you get 3 points, you automatically have a plane. So let's visualize for a moment this classroom. And we're going to take 3 points, okay? So we'll take the point over here in the corner by the door, top ceiling corner, okay? We'll take the point in the corner over there by that door, or by that window, right? And let's say that we take the point on the floor. What's the plane that would contain all three of those points? It would be a triangle if you connected them all, but the plane, that is where the triangle would lie, would be the wall behind me, right? The wall behind me, when viewed as a plane, would connect that corner point, and the point on the floor. And we could do that with, 3 points on the floor. The floor would be the plane. We do 3 points on the ceiling would be the plane. But it even works with the ones you can't see, that is because there's no floor, wall, or ceiling to connect them. So again, let's use the corner over there. Let's use the corner over there. And let's use the corner of the chalkboard right behind you. They still create a triangle, right? And that triangle would still live in a two-dimensional space. And that 2 dimensions it lives in would be a plane. So it doesn't matter where the points are, there's always going to be a plane that lies between, or lies in which the 3 points all lie. Okay? Exactly one plane as well. We name the planes by either the 3 points are on the plane. Okay, so you might call it plane ABC. Or there might be a Greek letter such as an alpha, beta, or gamma that's used. Okay. Greek letters are commonly used throughout geometry. We use them for a variety of things. I'll have a picture on my next slide of that, I think. Yes, I do. Coplanar points are points that are in the same plane. That's good. Right. Non-coplanar points are points that cannot lie in the same plane. So let's pause there for just a second and think about it. What the previous slide said was any 3 points necessarily have a plane that contains all of them, right? So in order for non-coplanar points to exist, you would have to have at least 4 points. There are no 3 non-collinear points, just like there are no 2 non-collinear, there are no 3 non-coplanar points, just like there are not 2 non-collinear points. You always have a plane between every 3 points, or with those points lying in them. So we need 4 points for them to be non-coplanar. And then coplanar lines are lines that lie in the same plane. So we're going to do some examples. If you take a look at this diagram right here, take a look and tell me if you can give me 3 coplanar points. Just give me 3. I don't have space to write. Okay, hang on just a second, sorry. Okay, and did you notice that I didn't even check to see if you were right? Do you know why? Because any 3 points will work, correct? Any 3 points will work. So now let's find your ACD on our diagram. Let's see, here's A, here's C, and here's D. Any other point in this blue region would also be coplanar with those 3 points, right? Okay, can you give me one additional point then that would be not coplanar that's in our diagram? B is one of them. So if we did A, C, B, and D, those are non-coplanar points. We also have coplanar lines in this diagram. Give me 2 coplanar lines. Yep. K would be, L would be, what else would be? M. So those are the ones that are written with the Greek, or not Greek, but with those italicized letters. You see those? It's not very clear, but you can see them a little bit. Can you give me one more line? Okay, fabulous. So AD would also work here. And if we're writing a line, we have to put the line symbol on top, okay? So any line that lies in this blue plane at the bottom would be coplanar. And AD would lie in it, and so would AC. And you'll notice, again, just by the nature of how we draw, we can't really draw the plane so that it shows that it's going in all the directions. Do you see that? Just like when we draw lines, we put the little arrows on the end to sort of indicate to us that it keeps going. There's not a real convenient tool for doing that with planes. So if it references this as a plane, our understanding has to be that the blue portion is just a portion of the plane and it extends in all those directions beyond, both ways. Okay? All right. Skew and parallel. Skew lines are lines that are not coplanar. So we found some coplanar lines a minute ago. Skew lines are lines that are not coplanar. And 2 coplanar lines are parallel if they do not intersect. So notice I don't have a diagram here, and the reason I don't is because it's really a lot easier to visualize, I think, in the classroom. So we're going to give some examples of skew lines in the classroom. All right, so the first line that I'll use is I'll use this line that goes from the ceiling up down to the floor with that corner. So you can picture that as being a line, right? That line will never intersect with the line along the back wall and the floor, right? Those will never intersect. They will never intersect. And they're not in the same plane. There's nothing I can draw to connect them all inside the same plane. And in part because they're sort of going in different directions, right? One's vertical and the other one's horizontal in a different, dimension. That doesn't work. Okay, so that's skew lines. In order for lines to be parallel, though, they have to first be coplanar. See, notice both of these don't intersect, right? Parallel lines don't intersect, skew lines don't intersect. The difference is whether or not they're coplanar. So in this classroom, we have lots of parallel lines as well. We'll use the same initial one here at the front, from the ceiling down to the floor along this wall. And we can use from the ceiling down to the floor along that wall edge. Those are in the same plane. It's the one that's behind me, the wall, right? But they don't intersect. And again, it's partly, and we can talk about it being, is because they're going in the same direction. They're both vertical lines, and they lie along the same, in this case, wall, our plane. Does that make sense? Okay, jot yourself down enough of that description in those 2 spaces you've got so that you remember what we just described as being the difference between these. And then we'll pick up with our examples next time.